Our group name is The Sims, and for our project we will be using the UCI solar airplane. Our group's goal is to study and run simulations on parts of the UCI solar airplane, specifically looking into the wing box, wing spar, motor mount, landing gear, and central beam. Each member's studied component is listed in the table.
The wing box is the primary load-carrying structure of the wing. In real life, the wood cracked at the outer cylindrical faces that interface with the carbon fiber rods. The wing box is simply supported at the center beam attachment areas, and some forces include the weight of the wings and front impact load. In the first iteration, all contact surfaces were chamfered slightly to simulate sanding. In the second iteration, the outer ribs to former attachments were changed from 90 degrees to 45 degrees. For every design iteration, 12 local interactions had to be changed, here, etc., requiring a lot of manual effort. FEA, it is found that the wing box can achieve 44% less displacement for 27% greater stress. If we assume a 4-month lifespan, 1 hour of daily flight time, and if 1 cycle equals 1 second, we have 438,000 cycles to failure.
The wing spar is the main structural member of the wing. It carries flight loads as well as the weight of the wings when on the ground. A static analysis and modal analysis will be performed. Simply supported boundary conditions were used. Fixed geometry was used on the top end of the spar and roller slider was used on the lower end of the spar. Gravity and an impact force were used for the static analysis, while lift and gravity are the loads being used for the closed form solution. The initial design is a 36-inch long round spar. The first iteration is a 36-inch long oval spar, and the second iteration is a 36-inch long square spar. The results tables show the difference between maximum stress and displacement for the 3 different designs as well as the modal studies. The initial design with the round-shaped spar had the lowest max stress and displacement. The SN curve shows that this type of steel has an 80-year lifespan. When this part is used 1 hour a day and 1 cycle equals 1 second, it will endure about 105,120,000 cycles at around 10 megapascals. For the closed form solution, we used the elliptical hollow wing spar, and this solution gave a value of 200% error compared to the SolidWorks simulations. The wing spar experiences large displacements, so therefore running a large displacement static study would help decrease the percent error.
The motor mount is located at the front of the airplane, which fixes down the motor and provides a means of propulsion. Some loads that are on this mount include weight of the motor, thrust force of the initial takeoff and constant airspeed, as well as temperature and vibrational loads from the motor. Some boundary conditions we have include fixtures on the bottom tap walls and bottom surface, and rollers on each corner for expansion. In the left iteration, we have no fins. As for the right iteration, we have an extended base and extended support fins. The results table on the top takes into account the initial thrust force, which is the strongest load applied to this mount. As you can see, on iteration 2, there is a 60% reduction in displacement as well as a 20% reduction in stress compared to the initial design. Assuming a 50-year lifespan for the ABS material, with 1 hour weekly usage, the part fails at 9,720,000 cycles.
The landing gear is the part from which the plane interfaces with the ground. From the initial to the first iteration, the corners were rounded out to reduce stress concentrations, and from the first to second iterations, the chamfers were also rounded out, while also reducing the length of the horizontal by 15 millimeters, which was the length on the underside of the landing gear that was unused. The landing gear is fixed at the spokes, with force of the weight, takeoff force, and landing force being applied to the top face. Max stress and max displacement were reduced by 15% from the initial to the second iteration, with the lowest buckling factor of safety being increased by a value of 2. Fatigue and modal results indicated that there wasn't significant changes, though it is worth noting that vibrations will have to be noted in order to avoid potential damage from resonant frequencies. In the SN curve, our values were unable to be plotted due to the low alternating stresses in comparison to the strength of the material, so we know that it definitely does not fail to fatigue.
The central beam is the structure that connects the front wing box and the rear wings. The split area in the front is the area that interacted with the front wing box. There are 3 loads for the beam: the weight force from wing box and other parts above, the lift force generated from wings, and the drag force from front. For the boundary condition, there are 2. One is both ends fixed, the split area on roller or hinge. The second one is both ends fixed, split area is fixed on the side. Here are 2 iterations. The first one is round beam, and the second one is a hexagonal beam. For the results, as we can see, the original beam with boundary condition 1 has the lowest max stress and the max displacement. here's model results. For the S curve, we can see that the beam can withstand the fatigue.